Right, level 3, line Y3, we're going to start talking about DC motors, excuse me, at this point. And one of the first things that we have to talk about before we get into DC motors is what motor effect itself is. And motor effect is just going to be a repulsion or an expulsion of my current carrying conductors out of a magnetic field. We're going to have a couple of things that are going to go and exist. First of all, we're going to need to go and have a field. Then we are going to need to go and have current carrying conductor. So conductor with amps on it. As long as we have those two, we're going to be able to go and establish what we will call our motor force. And it's going to be a force of repulsion that is going to try to remove current carrying conductors out of a magnetic field. Now we're going to learn all about motors, which are going to go and have a rotary magnetic field, which means we're never actually going to be able to go and remove them. Instead, we are going to continuously just be pushing them along through that motor field. Here's how the motor effect itself actually goes and works. What we're going to do is we are going to go and draw a conductor. Let me just duplicate this one over here and we'll add another one in. We'll start by drawing this in the path. We'll start by drawing this actually just as a set of poles over here. So I'm going to give myself a north pole and I'm going to give myself a south pole over here. And we know that existing between a north pole and a south pole, we are going to go and have magnetic lines of flux that possess a couple of different characteristics. One, they like to go and form complete loops, which means they're going to enter in here, they're going to travel back through the outside casing of the machine, the stator, back through to the other side. They possess that one. They also possess the fact that they cannot go and cross each other. Magnetic lines are not able to cross. And last of all, magnetic lines are going to go and possess a force of elasticity, which means that they are always going to stretch as tight as they can, but they are able to be stretched in other circumstances as well. We're going to see that happen over here when we go and insert a current carrying conductor. Let's go and take a look at a current carrying conductor over here. If I take a look at a current carrying conductor, we'll take a look at two separate current carrying conductors over here actually. One of them I'm going to have the current that's heading away from me. It's going to be indicated by the cross. The other one I'm going to have the current that's heading towards me, indicated by the dot. You should be familiar with your left-hand rule at this point and should know that if you use your left hand, stick your thumb in the direction of current, that your fingers curling around will show you the direction of my field. So this over here is going to have a field rotating like that. And if I go to the other one, my field is going to go and be rotating around like this over here. All based upon just the type. The size of the current that we're going to have is going to determine how far out these are going to go and push. But even if it's just a tiny bit of current, that tiny bit of current is going to go and have magnetic lines of flux that cannot be crossed by other magnetic lines of flux, namely these ones that we're going to have over here. What I want you to envision right now is that this stuff over here is rotating really, really, really quickly. At this point, you've been in the field a number of years, so you should be quite familiar with what happens when we've got rotating machinery and something gets caught up in it. Imagine you're drilling through studs, you got the whole hog out there, and if you have got a scarf or something like that, if anything enters the direction of rotation, the direction of whatever is rotating is going to pick it up and it's going to go and tear it around in the same direction, right? It's going to wrap it up in the same direction as what it is going. We get the same thing that happens with our magnetic fields when we go and insert this into here. If I take this conductor and drop it down here into the center, we'll put that like that, it's going to go and have its magnetic lines of force going around this conductor that are going through like that. What does that do to the main field? Well, it is going to go and distort my main field. Let's take a look. My north pole, I'm just going to draw some green lines over here to represent what's happening. So normally we would have blue, but my north pole is going to be exerting lines. Those lines are going to get picked up and torn around and then pulled back in to the other side. And we're going to get that with all of our lines of flux. They're going to get picked up and they're going to get torn around. What I have created at this point is nothing more than a slingshot, where I have got these lines of force. Remember, they possess elasticity. I've now stretched them back like having a rocket in, which means that what they're going to try to do is they're going to try to go and expel this current carrying conductor out in that direction. If we were to change the direction of current going through that conductor, just do that real quick. that. If we were to go and place the other current carrying conductor inside of here, so now it's going to be the one with the current traveling away from us that has got its lines of flux traveling around and around and around like that, what we would see is, once again, my lines of flux are going to go and leave from my north pole. As they do, they're going to get caught and torn around, and then they're going to go and leave and go back to that south pole that's going to be over there. Any of my lines of flux are going to go and do this, which once again means that I have got a rubber band, an elastic, a slingshot over here that is being pulled down, and the direction that it's going to want to repel this conductor is going to be just straight up. Boom, out like that. Can I make the motor effect any better, any stronger? Absolutely. There's a couple of things that I could do to make the motor effect stronger if I wanted to increase the amount of force that I'm going to go and get out of it. One of the things that I could do would be increase the number of field poles. It's like having more elastics that are going to go and be stretched across from here to here, which is going to give me more of a force pushing out. That's one way to do it. The other way to do it would be to go and dump more current through my current carrying conductor. Let's add a bit more current going into here, which means that there's going to be more lines of flux going out and around, which basically means it's going to go and have a larger distortion, so that the lines of flux that go around it are now going to get pulled much further around. So we are going to have a bigger force around here. Increase either the magnetic field that it's in, or increase the amount of current that is inside of that conductor, and we will ultimately go and get the force that is going to go out. Okay, I want to note that we had two things that we went and found before we found the third. First thing that you should note is that we found our direction of field over here. We had to see that field. We also had to see our direction of current that we were going to go and have inside of here before we could go and actually see what we had for our thrust that was going to be sticking up, pushing out of here. We're going to go and use all three of those, field, current, and thrust, when we go and take a look at Fleming's right-hand motor rule. We have dealt with the left-hand rule. We are now going to deal with the right-hand rule. Once again, do not mix your hands, your left and your right. We're also going to go and start with only two of our digits that are going to go and be extended. The very last thing that we developed was going to go and be my thrust. So what I'm not going to do is I'm not going to start with my thumb in there. Okay, keep the thumb folded down until you have established the other two. We need to know the direction of the field, north to south. We also need to know the direction of our electron currents, how the electrons are flowing through the conductor. That's what this one is here. Through. That's how I spell that. No, that's not how I spell it. It's spelled like this. Through. Conductor. Okay? So we need to know the direction of electron current that's going to be traveling through the conductor. We need to know the direction of the field. And once we establish all of that, then we can unfold our thumb and figure out what the direction of motion is going to go and be. Let's go back to this illustration number 1, where they show us the motoring effect over here. Once again, we are going to go and start by establishing our first finger in the direction of field, right? F is for F, field is for first finger, center finger is for current over here. So we are going to go and establish our field. First finger should be going across from north to south like that on your right hand. Then we are going to go and establish our direction of current. Our current is heading into the page over here. It's the cross that we're seeing over here, which means that I'm going to go and have my center finger pointing down and into the page. With your first finger going across from right to left, or from left to right, and your center finger going in, you can now unfold your thumb. You should see that your thumb aligns with this force over here. If it doesn't align with that, you're doing something wrong on all of these. It should align with that to go and push that out. Okay, how does that go and drive a motor? Because what we see over here is that it's going to go and push this thing out, and once it gets out of the field, we would no longer have any sort of a force on there. Well, what we need to do is we need to provide a continuous force. The way we do that is by putting our motor onto something rotary, right? We're going to have our stator and a rotor, and we're just going to go and wrap this thing around. Let's take a look at our conductors inside of here. And now we are not going to go and have a direction of rotation. We're going to establish a direction of rotation. Let's start with our field. We're going to examine this thing only at one side at a time, okay? So we're going to start with the left-hand side over here. The left-hand side, what I'm going to go and see off of it is that I have got my field that is traveling through from there, traveling through there, etc. So that's going to be my magnetic field, my first finger. I'm going to go and have my center finger, which shows me I've got current traveling into the page on all of those. So what I'm going to go and do is I'm going to stick my first finger in the direction of my fields. I'm going to go and stick my center finger in the direction of my current. Make sure you're doing the right-hand rule here. And then I'm going to go and stick my thumb in the direction of thrust. And I see that for everything on this side of the line, the thrust is going to be going up. We'll do the same now on the opposite side of the line. We're going to go, once again, right-hand rule. First finger in the direction of the fields, center finger in the direction of current. So now your center finger should be pointing up towards you, thumb in the direction of thrust, and you're going to see that for all of these, the thrust is going to go and be downward. So what we're going to have is that on this side over here, we're going to have that central axis over there. On this side over here, it's going to be pushing up. On this side over here, it's going to be pulling down simultaneously, which means that we're going to go and get rotation, right? Anytime that you've got something that's fixed in the middle and one side is pushing up, the other side is pushing down, you will get rotation. We are also going to need to have something that is going to go and change this direction of current as it crosses, because if I kept this current going through like that, when it crossed over to the other side, we would start to go and develop thrust in the opposite direction. Our motor would go and stall out. So what we are going to go and have is we're going to go and have a commutator. Once again, what is a commutator? It is a rotary switch. And what that rotary switch is going to do is as we cross this over here, we're going to go and call this the neutral plane. As we cross that neutral plane, we are going to go and switch the direction of current going through the windings, which is then going to go and allow us to maintain the same direction of magnetic flux, the same force that we are going to go and have off of this. Remember, a commutator is nothing more than a rotary switch. When we use a commutator on a DC generator, we use it to switch the generated AC into DC on the output. When I use it inside of a DC motor, I'm going to use it to switch the DC that is coming in and make it go in the opposite direction. Basically, it's going to go and convert from a DC into an AC, because my conductor inside of here is going to go and have a AC. It's going to change its direction that it's going to have. I should actually draw it looking like this over here. Right now, its direction of rotation, we're forcing this thing up like that. We're going to have current that's going to be pushed through it like that. I've got current traveling through there, and it is going to go and move up, up, up. Eventually, I'm going to get up to here. And once this thing goes and crosses and moves around to here, then we would have to go and reverse that direction of rotation through that same conductor in order to go and maintain the same sort of magnetic field that we would have off of it. Okay, armature current is also going to go and give us a little bit of armature reaction. We talked about this when we were looking at DC gensets, that armature reaction is this thing that happens where I'm going to go and create a north and a south on my armature itself, just based upon the way that I have got my currents themselves traveling through there. I want you to go and take a look at your motor that you have over here, and wrap your fingers going through. Use a left-hand rule over here. Drive your fingers going through the back and around to the other side. And if you do so, you should see that your thumb is going to go and form a north up at the top over here, which would mean that we would have to have a south down here at the bottom. What that means is that I am going to go and create an artificial small south pole at the bottom that is going to join with my other south pole to create an overall larger south pole. I'm going to go and have a north pole that's going to go and do the same thing. An artificial north pole from my armature that's going to go across there. And what I'm going to see is that my armature is going to go and move from having a neutral plane that's physically vertical. My neutral plane is going to go and start to twist off towards the side over here. Okay. Your binders do have this relatively useless picture inside of them over here. And this picture tends to cause more harm than it necessarily does good. I'm going to quickly explain it just so you understand what they're trying to go and do with it. But it really doesn't go and show us a lot other than that we've got a differing direction of current. Are my DC machines more or less the same physically? Absolutely. Whether we're going to be looking at a genset or whether we are going to be looking at a motor, they're going to be made out of the same types of components. We're going to have our field poles. We are going to need to have our commutator, armature, and bells, bearings, all the rest of that stuff. On every given machine, there's going to be two things that we are going to supply into the machine. and then one thing that that machine is going to go and supply out. Over here for a DC generator, we are going to go and supply the fields. That's going to be one of the things. And we are going to go and supply the rotation. And if we supply a field and rotation, then we are going to go and generate current. That's going to be coming out of our armature itself. If I am going to go and take a look at a DC motor, we are going to go and supply the fields. And we are going to go and supply armature current, and then as a result of that, we are going to go and get rotation. We're going to get thrust out of this thing that we can then use to, drive out towards any loads or anything like that. What they're showing inside of here is that if I have got a DC generator and a DC motor that are going to be traveling in the same direction, the current that is going to be traveling through the armature is going to be opposite to each other. It really doesn't do much for us to know this fact that the current is going to be opposite. They're just trying to relate this to the fact that one of these is a source. That's going to be my generator set over here. So Jenny is a source, and this one over here is going to go and be a load. That being said, if I were to go and take a look at my two terminals over here, I'm going to have two terminals over here. We're just going to call those, two sides of the commutator. We should be able to go and take a look and see that our directions of current are going to go and have something that is comparable over here. Let's start with our load. Our load, we know that current flows from negative to positive through a load. And we know that for a source, current flows from positive to negative through any sort of a source. So all we need to do over here is we need to go and say if it's going from negative to positive, that means my current is traveling through here. This would have to be my negative side. This would have to be my positive side over here. If we were to go and take a look at this, current flows from positive to negative. My current is flowing through in that side, which means that I would have to have a positive here and a negative over here. They're showing that for the same polarity, positive, negative, that we would have off the commutator, that we're going to have actually opposite directions of current that are going to be inside here. But they are opposite machines, so this just kind of goes and makes sense. One is taking in electricity to go and create motion, rotary motion. The other one is providing rotary motion to go and create that electricity. Okay, reversing rotation. Reversing rotation, we can go and interchange anything on our right-hand rule. We can change the direction of the field flux. We could do that by interchanging the magnetic polarity of the field poles. Or I can change the direction of my armature current. That would be my center finger that I would be able to go then return, which would reverse my thrust off of that. The more common way to go and reverse it is going to be to reverse the armature, because my coils, my field coils series or shunt types of fields, in some cases we're going to have compound wound motors. If I have got a compound wound motor, that compound motor is going to need to have all the windings changed. If I only change a couple of the windings, maybe my shunt windings, and I don't change my series windings, I'm going to go and change it from being, possibly a cumulative compound into a differential compound. It will have a completely different aspect to the way that it's going to go and operate. So rather than screwing around with, which one do I change, I'm going to usually go and change the polarity of my armature. Okay. Talking about this one over here, where they're talking about main field distortion off of these. Main field distortion is just going to go and be something that's going to happen, that armature reaction. We did talk about armature reaction that happens inside of a DC machine. That armature reaction is going to go and happen just because we have gone and distorted the actual direction that thing is twisting. I know I've skipped quite a ways ahead inside of here. We're going to come back to some stuff here in a minute. Right now we're just going to finish describing the physical before we go into the rest of this stuff. The armature reaction is going to move us from being at a true neutral plane that is both my electrical and my mechanical. It is now going to go move my electrical neutral plane down and out of here. And it's just happening because we are going to go and create small fake poles that are going to exist at the top and at the bottom of our mechanical neutral plane. This can be counteracted. We've got a number of different ways that we are going to be able to go and counteract them. One of them is going to be to use interpols, which are going to go and be small poles that are going to be placed in between my main poles. We see main poles in this illustration over here, and we see interpols, which are going to be these two over here. The interpoles are going to be wound with a conductor that is carrying the main armature current, so that once again they are going to go and have the same value of flux that we are going to go and have. They are going to be different than the gensets in that our motor interpoles have to have the same magnetic polarity as the main pole directly behind it with respect to the direction of rotation. For a genset, it had to be directly ahead of it. And we just connect them in series with that armature so we can go and carry these through. We are going to go and use these things heavily just because we get such bad distortion otherwise. Interpoles are relatively easy for the manufacturers to go and place into there, and they really do up the efficiency of their motors, so they're going to go and place them in quite heavily. Compensating windings are going to be the same as compensating windings that we took a look at inside of our DC generator, where we're going to go and put them into milled slots in the faces of our main poles. They're very expensive to go and place in, and so we're not going to go and use them in a lot of cases unless we have got DC motors that are, part of a critical industry where we're going to go and have sudden changes. Things like a rock crusher, where it might be crushing small and all of a sudden, boom, you get a heavy piece of, iron ore going through or something like that. Those would need to go and have them inside there. Okay, that's most of our physical talk about these things. Now let's start talking about the actual theory about how these things are going to be developing differing values of torque, counter EMF, and starting current, etc. First of all, let's go and define what torque itself actually is. Torque is going to go and be a twisting action that I'm going to go and have on any sort of a motor. We'll go to this one. We'll go to this one over here. We'll use this one for our illustrations here. Torque is going to go and be a twisting force that is going to go and happen on any sort of a motor. And it is going to be defined by a formula. That is going to be for a motor over here. I'm just going to write motor up top here. Torque is equal to K phi I over here. Now, this is really similar to another formula that we took a look at it in gensets, and we'll just put that one up here just for point of reference. For on a genset, we would go and have that my EG is equal to K phi N over there. Both of these have got a K inside of them. K is going to go and be my constant for the actual machine itself. Is going to be how this thing has been built, the amount of air gap, the types of windings, lap, wave, the resistances of the wires, all of that stuff goes and gets combined together in the form of value that's called K. We don't have to calculate K, we just have to know that K goes and exists. I is going to be my armature current in amperes, and then phi is going to be my flux or my excitation that is going to go and be in Webers. Really, when we take a look at this formula up here, this is going to go and be defining my field. Actually, I'll just draw it out over here. That is going to be these blue lines, which are going to be my field strength. I is going to go and be my conductor currents. These over here, that is going to go and be my I. So the increase in either one of those, either I'm going to go and have an increase in armature currents, which is going to go and cause bigger circulating magnetic fields, which is going to go and distort it more, provide more thrust. Or if I go and provide more main field, the blue lines over here, that's also going to go and provide more thrust, more torque off of it. The K stays the same for these ones over here. My torque is always going to go and stay constant off of a motor. Well, I shouldn't say it's going to stay constant, but it more or less is going to go and stay constant. And it's going to be always determined by what I have got for mechanical load. When my motor is not loaded very much, at no load, I'm only going to go and have a very tiny amount of current that is going to go and run through there. Therefore, I'm only going to go and have a very tiny amount of torque that I'm going to go and run through there. If I'm going to be running that motor at full load, where I've got this thing, turning something out there in the field, then my current is going to be high. It's going to be at a max, which means that my torque is also going to go and be at a maximum. And it's going to be adjusted just through the action of something that is called counter EMF. Now, you talked about counter EMF back in second year when you started going through transformers. Hopefully you still remember what counter EMF is. Counter EMF is just going to be a buildup of voltage that is caused by cutting action. EG is equal to BLV. That is going to go and happen where we are going to go and have counter EMF inside of a conductor. This happens inside of a conductor. It also happens inside of things that are made up of multiple conductors, transformers and motors, which are really just a rotary type of transformer. That counter EMF is going to go and fight back against my main applied value of voltage. And what it's going to do is it's going to go and give us a net value of voltage. If this is my applied value of voltage, my counter EMF is going to go and fight back against it. This is CEMF, CEMF, which is going to go and give me a relatively small net value of counter EMF over here. Does this make sense to you? I hope so. Where does this counter EMF come from? Well, the counter EMF is going to go and come from another formula over here, which is going to be EG is equal to K phi N. EG is equal to K, constant of the machine, phi N. Wait a minute. This is the exact same formula as what we had for my genset. And it is the exact same formula because anytime that I am rotating conductors inside of a field, look, the motor action is causing this thing to go and rotate, but that means that now I've got conductors that are rotating inside of a magnetic field. We are going to go and have generated voltage. And that generated voltage is going to go and be opposite to my applied voltage. Remember this drawing over here where they're showing the directions of current caused by a source compared with caused by a load. This is going to be my load when this thing is acting as a motor. This is going to be it as a source when it's acting as a generator. So I can see that any sort of a current that's created as a generator is going to be in opposition to any sort of a current that is existing as part of its drive as a motor. This is really, really important that we understand this. Because this is really going to allow us to go and view another formula in the correct light. This next formula has got a few more letters inside of it, but then we're going to be able to go and take the letters that we see inside of here and we're going to be able to actually drop them down into a smaller, or simplify. I'm just using Ohm's law. Let's start by writing out this next formula over here. The next formula is going to go and be my E armature is equal to my E applied minus my E generated. Okay. This is different than the formula that you have in your book over there because yours has got a E applied, it has got an E generator, but it does not go and say armature voltage. What they have inside of the book over there is they've taken the armature value of voltage and they've broken it down into a smaller formula, which is going to go and be my IA, the current through the armature, multiplied by my RA. That's all that they have got for the armature value voltage. But if E is equal to I times R, so if it's the armature resistance and if it's going to be the armature current that is going to be inside there, what they're giving us is they're giving us the effective amount of voltage that we have on the armature itself. After the counter EMF, the generated value of voltage has been taken away from our applied value of voltage. We also can go and expand this one over here. My E generated is going to be equal to my K, phi, and N over here. E applied, well, we're just going to leave that one alone as is. But we're going to go and now work with all of these expanded ones to go and talk about motor starting current, and then about mechanical loading, and then about locked rotor conditions that we are going to go and have off of these. Let's start talking about what we have when the motor is sitting at a standstill. Okay, we're going to go and take this. We're going to go and just remove a whole pile of these lines over here. When the motor is at a standstill, my value that I'm going to go and have for rotation, RPM, is going to be at a value of 0. If that's going to be at a value of 0, then that means that this whole formula, E gen, is going to be at a 0, which means that my full applied value of voltage, let's go and say that this thing is going to be, I don't know, 120 volts DC. I would have 120 minus 0, which would tell me that I would be dropping all 120 volts over top of my armature. And if my armature has only got a small value of resistance, let's say that the resistance is 2 amps, that would mean I'd be dropping 120 volts over top of 2 amps, over top of 2 ohms, which would mean that I would go and have 60 amps of current that I'm initially going to go and have flowing through here. So the very initial startup would be a very, very large value of current that I'm going to have through here. Very, very large value of current through here, which means that it is going to go and greatly bend these magnetic lines of force as it's going through there. Because it's going to go and greatly bend them, we're going to start to torque up. So this motor is going to start to push because we have, gone and distorted these ones. As that motor starts to go and push and rotate, this value of N over here is now going to go from 0 into a value, and it's going to start to go and rise. And as my speed increases, what I'm going to go and see is that my generated value of voltage inside of here, because remember, these are rotating conductors inside of a line of flux, so they are going to be generating. As they're going to be generating a value of voltage, this value of voltage is going to be going up. Let's take it up to, let's say, 30. If we brought it up to 30, that would mean that this 120 minus 30 would mean that we would now be down to 90. And if we were down to 90 as being my armature value of voltage, and I've got 2 ohms of resistance, we would see that this thing would now have dropped down to 45 amps. And then if we continue to go and speed up, we are then going to go to a, what N increases, my generated value is going to go and increase. Let's take this thing all the way up to a value now of 60, which would mean that 120 minus 60 would mean that I've got 60 now that I'm going to go and have on my armature, which would mean that 60 divided by 2, the resistance of that my armature current would now be dropping down to 30 amps over here. So what we see happening is that when we initially start up, we're going to have a massive slug of current that is going to go and enter our motor over here, because the only thing that was limiting the amount of current that was flowing in was this tiny little bit of armature resistance. But then as my motor started to come up to speed, we saw that initial value of high current that went and dropped away until it's going to go and stabilize at some lower value of current, whatever my running value of current is going to go and be. We have to be very careful when we start motors up just across the line or applying full values of voltage to them, because if I apply full values of voltage to them, I can get some massive, massive, massive amounts of current that are going to go and slam in through there. This creates huge magnetic stresses inside of that motor, as well as it's going to go and cause brownouts in other parts of your system. So we want to limit the size, generally speaking, 2 horse and under. We're fine to go and start them across the line, but by the time you start getting up into your 3 horse and going up, especially 5s, etc., you need to go and use some sort of a way to go and attenuate the amount of current that is going to be coming into there. So usually what we will do is we will drop the applied value of voltage in a couple of different ways. We can go and stick resistance in front of there. We can go and use SCRs in front of there. We can go and use, all sorts of different things to go and reduce the value of voltage as we start out, just so we reduce our current levels down to something that is going to go and be safe. These are going to be called reduced voltage starters. We're going to skip past locked rotor. We're going to go over to mechanical loading for a second. Then we're going to come back to locked rotor that are going to go and be inside of here. Mechanical loading is a really incredibly cool thing that is going to go and happen inside of a motor. And basically, it is going to go and show us how a motor is going to go and work its little heart out. Okay? Motors, whenever we ask them to go to work, those motors are going to go and work their hardest. So we are going to mathematically go through that right now. Let's start with talking about a motor when we start to load it down. Well, when we start to load down a motor, that increase in mechanical load is going to cause my speed to go and decrease. When my speed decreases, that causes this whole thing, my generated amount of voltage, to go and decrease, my counter EMF that I'm going to have inside there. Because my applied voltage stays the same, we'll just lock it down by putting it in the box over here, because that applied voltage stays the same, and we've got less generated voltage now, counter EMF, that means that we're going to go and have more armature voltage. That is going to go and be dropped across the actual armature. If we have got a greater armature voltage, and because my armature has only got a fixed value of resistance, that would mean that my armature current would have to go up. And if my armature current has gone up, then we can go and apply that to another formula. Let's just add the last formula down here, which is going to be my formula for torque. Torque is equal to K phi I. So if my armature current over here went up, that would mean that this would go up, which would mean that my torque would go up. So I'm just going to go through it again really quickly. I apply load, my speed drops. After my speed drops, that is going to cause my counter EMF to go and drop. Because my counter EMF dropped, my armature value of voltage is going to go up. If my armature voltage has gone up, that would mean that my armature current has gone up because the armature resistance was fixed. And if my armature current went up, that would mean that my torque that I'm going to go and output is going to go up as well. And so we're going to go and have this increase in torque that's going to go and counterbalance that increase in load that we had. If we continue to go and add more and more and more load onto the motor, we won't be able to go and work out this path. The motor's going to keep trying, but eventually we're going to hit this point where we are going to have too much load and the motor is going to go and stall. And when the motor goes and stalls, that would mean that I'm going to go and have a value at that point that will go and change. Instead of this from being a low value, it's going to turn to 0, which would mean that my generated value of voltage would be at a value of 0, which would mean that I'd be seeing full applied voltage across my armature because we're subtracting nothing, which would mean that I would have a massive amount of armature current equal to my inrush, which, although it's torquing, although it's trying hard to get started over there, is not able to go and overcome whatever our load is. So what we should have is we should have something that is going to go and read that value of current. Ooh, that did not work out well. That is going to be reading that value of current and respond to it. And that's going to be your overloads inside of a motor. Overloads are supposed to go and respond when we hit that point called the locked rotor condition. A locked rotor condition is where the rotating part, the armature of our motor, has been tied down by mechanical load. Usually, it's something that develops slowly over time. You're going to go and have a heavy load on the system, then your customer usually goes and pushes the boundary with exactly how much they can go and take out of it, and then they don't do proper maintenance. And so you start having mechanical friction that really starts to build up. Every single roller along, a big roller chain hasn't been, lubed in a couple of years, and so you get all this extra friction and drag on there, and eventually this thing just causes us to go and stall out off of there. When we're talking about this whole thing about, when we go and increase torque, we should also talk about what happens when we go and decrease the amount of work that we are taking out of a motor. If we were to go and decrease the amount of work that we were asking from a motor, so we were to take some load off, we would go and see an increase in our speed. If we see an increase in our speed, we're going to see an increase in our generated voltage, which would mean that we would see a decrease in our armature voltage, which would mean we would go and see a decrease in our armature current, which would mean we would see a decrease in our torque over here, because that's all going to go and be related. So motors are just this wonderfully, built thing where all these laws of science work together to go and cause this thing to respond to changes in load. They will try their hardest. They will work until they go and burn out, because as we just continue to increase load, we go through this path just in the opposite direction, and we're always going to keep going until eventually we get to that locked rotor, to that stalled motor, which is never going to be, a good thing for our motor. Okay, let's talk a little bit further about torque and horsepower at this point. They give you a bunch of formulas over here where they talk about what work is. Work is going to be force times the distance that we are going to go and have. Looking at that formula they give you, they say work is equal to F times 2 pi r. 2 pi r is just going to be the way that they're saying that, look, it's going to be force times the distance, and the distance is going to go and be my circumference of the armature it is. So work is going to be defined by that. Then we're going to go and take that work, we're going to put it over top of a second, and that's now going to go and tell me power. Power is the amount of work I can do in a given amount of time. Everybody can do work, just some people can do work faster, and therefore they're considered to be more powerful. Same thing goes inside of all of our machines, etc. Okay, so what we're going to be able to do is we're going to be able to go and combine a bunch of these different formulas together as we go and tie these different formulas together, we're going to go and see this change into what we call our horsepower. And horsepower was actually developed off of James Watt's originally taking a horse and making a horse lift stuff and saying, I know how much a horse can lift. Now we can go and say that this motor is equal to, the work of 1 horse or 2 horses, etc. And that's where this whole thing came from. They take that previous formula over there, the 2 pi t and n for rotation, and my t, that is going to go and be torque, my torque and my speed. They then go and combine it with a bunch of other numbers until they get to this thing where they are able to go and say that my power is going to be, or my horsepower is going to go and be equal to my torque times my rotations. This is horsepower. They don't have it in front of there, they're missing it from the front, is equal to my torque times my rotation, my RPM, all over top of this constant of 5252. I'm not going to go through all the math that they took to get these steps because they're just showing you all the steps that it takes to go and get there. This is going to go and allow us to take any value of torque that we can go and measure, things like torque wrenches, etc. We can use them to figure out how much force it takes to go and rotate something. Then we can say, well, it takes that much force and that we need to go and rotate it at this speed. Once we know the force and we know the speed, we can then go and multiply those two together, divided by 5252, and it's going to tell us what the horsepower is going to be necessary to go and drive that. Guys, this is not just a formula. This is something that you can actually do on a job site. If you're looking at something and you're like, I have no idea how big of a motor I'm going to go and need. You can actually throw torque wrenches onto stuff instead of just guessing at your motors. Stick a torque wrench onto it and then just start to go and turn it. Now, if it's a geared down system, you're going to be able to go and turn until you start to figure this thing out. Then you'll figure out your RPM past that, and you can figure out the horsepower that you need to go and drive that. There is this other constant that is also there, which is going to be that 1 horsepower is going to be equal to 746 watts. You should have that one memorized now at this point. Okay, speed regulation. Speed regulation is another formula that we deal with when we are looking at our motors. And speed regulation looks very similar to our voltage regulation. You guys remember looking at voltage regulation inside of the gensets? This is now going to be looking at our speed regulation, but it's almost the same formula. It is going to be no load minus full load over top of my full load. So we're basically going to go and say that, look, when a motor starts up, the motor is always going to start high, but then as we load it up, its speed is going to go and drop, right? So that's going to be my N and L, no load, and this over here, if this is going to be my full load, this would be my N full load, and FL that we would have over there. We combine these into a formula and we just say how much is this compared to the rest of this, and it's going to go and give us a percentage that we would go and have for these. Percent regulation for speed, NL minus NFL all over top of my full load that I would go and have over here. DC motors, depending upon the type of the motor, are going to either have really good speed regulation, or in some cases they're going to go and have crap speed regulation. They have smooth operation, but they don't necessarily have smooth speed regulation. We're going to see some of them where we have got really great torques, but we don't have great speed regulation, etc. Okay, base speed. We got to go and talk about what exactly base speed is. So base speed is going to go and be what a motor itself is rated at. When we have got a motor that's going to be 900 RPM, the base speed doesn't mean the lowest speed it can go to. It's going to be what this thing is rated to go at. So 900 RPM would be the base speed of a motor that has that on its nameplate. Now, power is going to be proportional to the product of my torque and speed. We see that off of this formula that we have right over here. If I have got an increase in my speed, if I get an increase in my torque, I'm going to go and see an increase that I'm going to go and have in my power. If I go and operate my motor a bit high or a bit low, I'm going to go and change the amount of horsepower that I'm going to go and have out of this thing. So if I can go and make it go faster, go above base speed, what I'm going to be able to do then is I'm going to be able to deliver more horsepower out. But if I go and make it go slower, I'm going to go and get less horsepower that is going to go and come out of this. All right, so my current that I'm going to go and have inside of my motor is a function of my counter EMF that is developed by the armature. Whatever I get inside of here, the amount of current is going to go and be that that armature is going to be based upon what I have for my counter EMF over here. If I go and place a rheostat or a control device in my field circuit, so here's my field over there, and if I were to go and limit the amount of current that was going to go through there, then my field current is going to go and decrease. And if I go and get a decrease in my flux, erase a bunch of little arrows over here, that decrease in my flux is going to go and mean that my generated value of counter EMF is going to go down, which would mean that the amount of volts that I would be applying to my armature would be seen as going up, which would mean that this value, my armature current, would be seen as going up as well, which would mean that I'm going to go and have more torque out of this thing. I'm going to go and have more speed out of this thing as well. Although we do lose a little bit of excitation by dropping the current that is traveling through this over here, there's still going to be enough residual magnetism that's going to be left inside of here that it's going to be able to go make up for it. So although we lose the excitation, we are going to go and get more torque to go and make up for it, which means that I'm now going to be able to go and operate above that base speed. If I would continue to go and increase my resistance inside here, just think about the largest value of resistance that you guys can think of, and the largest value of resistance you can probably come up with would be an open circuit, right? Where that circuit itself has gone and pulled all the way open. If that circuit pulls all the way open, then we are going to go above base speed as well. We're going to talk about that later on. It's going to be called losing the field when we're looking at our shunt motors, which is going to go and be operation above base speed. If I want to go and operate below base speed, I need to go and control the amount of current that I'm going to go and have going through these conductors over here. If I can go and insert some resistance into the armature and thereby drop the value of current, they're going to go and have smaller fields around them. If they're going to go and have smaller fields around them, we're going to go and get less torque out of this thing, less twisting action that we are going to go and have out of this motor, which would mean that it is not going to be able to go and spin nearly as quickly. So we are going to go and be able to drop below base speed. However, because it is going to go and carry all of our armature currents, and because that's the largest current we have inside of a motor, it would mean we would have to have a massive rheostat, which can get to be, very expensive. We're talking about rheostats that give off the same type of heat as what you would have off of a baseboard heater. In a lot of cases, we are going to go and not use resistance. Instead, we will use semiconductors. We've got a whole pile of different semiconductors we covered earlier in the A6 unit that we can use to go and build different types of basically voltage controls for these things. And we'll cover some of that stuff later on once we get into our different types of DC motor controls. Okay. Past that, they then moved on to those pictures you guys had of interpoles and armature reaction. We've talked about that before, so what we're going to do now is we're going to start to go and do some calculations for all of my different types of DC motors. We're just going to move this drawing a little bit off to the side over here. We're going to come to that one in a second, but we're going to start with the first example that they give you, where they've got a 240 volt motor that is operating at full load with a counter EMF of 22 volts. And then if the resistance of my armature is 1.5 ohms, determine the armature current. This one, if I apply 240, so my E applied minus my ECEMF is going to go and equal my E on my armature. Okay? So if I have got 240 volts applied, but I fight back against that 240 volts with 222 volts of counter EMF, that means that I'm only going to go and have the distant difference. That is going to go and become my applied value, which would be a difference of 18 volts. I'm going to have 18 volts as my armature value of voltage. If I know my armature value of resistance, 1.5 ohms, I can figure out my current. I is equal to E over top of R. So if I've got 18 volts on my armature, and if I've got an armature resistance of 1.5 ohms, I'm going to be able to go and take 18 divided by 1.5, which is going to go and give me a value for current of 12 amps. When I would start this motor out, I would have a much larger amount of current, right? Because this is what we have once we get the full counter EMF. What would be my inrush on this motor? Well, my inrush on this motor would be when I've got 0 counter EMF, which would mean I'd be applying the full 240 volts across that 1.5 ohms over there. We can do that to see what that would be. Let's say if our starting out, our counter EMF is at 0 because we have no rotation, I would have a full 240, and that 240 volts would be over top of 1.5 ohms. So we'll just place that over top, 240 divided by 1.5, 240 divided by 1.5 gets me to a value of 160. So initially starting out, this thing is going to go and take in 160 amps. So when we turn this motor on, we're going to get this massive spike up to 160, and then it is going to go rapidly drop back down until we get down to this value of 12 amps. This is not to scale because 160 should be 10 times larger, but that's what my startup would look like for this motor. A massive inrush that's going to taper off relatively quickly once we come up to speed. Be damaging amount of current to go and take into anything. So we, once again, are going to want to look at doing some of those reduced voltage starting methods that we're going to find out about a bit later on. Okay, next example that they give us is this one over here, this drawing. I'm just going to erase all of this over here. Down and delete those. Okay, next one that they're going to have is going to be this long shunt 240 volt compound motor. Now we haven't gone and taken a look at the difference between short shunt and long shunt yet, but we're going to go cover that stuff later on. Long shunt just basically means it's going over top of the combination of the armature and the series field. We covered that inside of generators. It means the same thing inside of my motors over here. But they're telling me that I'm putting in 240 volts and that I am drawing from my line over here 20 amps. Okay, so we got 20 amps of line current over here. They do give me a couple of values of resistance. This is the resistance you could have found when the motor was stopped by disconnecting and measuring each one of my windings. I'm going to go and have an armature value of resistance. That's going to be 1.2 ohms. 1.2 ohms over there. I'm going to go and have a series field of 0.6 ohms. And I'm going to go and have a shunt field of 120 ohms. I don't know if you remember at the very beginning of when we were looking at our DC machines and generators, there was those drawings that showed the series and the shunt type of windings, or they were actual pictures, and you could see which ones were my series and which were my shunt, because the series were going to be fewer turns of thick wire and the shunt was many turns of fine wire. So our shunt is always going to have this higher value of resistance. All that we need to do is KCL this circuit, Kirchhoff's current law, to it. So I'm going to go and say I've got 20 amps coming in. I'm going to go and take some amps off over here, and then I'm going to go and send the rest down through here. We can go and say 120 volts, I see I've got, or 120 ohms, I got 240 volts over top of that. I is equal to E over top of R. I have 240 volts over top of 120 ohms for this over here. Therefore, I'm going to go and have a current of 2 amperes. 2 amps that we are going to have over there. Well, if I had 20 that was entering this node and I took 2 out over there, that would mean that now I'm left with 18 that is going to be entering in over here. If I want to go and figure out my value of armature currents, my armature and my series are going to be in, our armature and series field are in series, so both of these are going to go and have 18 amps that are going to be traveling through them. This is going to be 18 amps, and this one over here is going to be 18 amps as well. If I have got those, I can figure out what I've got for armature value of voltage. Let's quickly go and do that. V is equal to I times R, so I can go and take 18 amps multiplied by 1.2, which gets me to a value of 21.6. I see that I have got 21.6 volts that I'm going to be dropping across here, which would mean I must be dropping the remainder across here, right? We got that 21.6 that we're going to be dropping across this section over here. I must be dropping the remainder across here, so we can go and figure out what that value is. 240 minus 21.6. Gets me to a value of 218.4 that we are going to go and have over here. to 18.4 that we are going to go and have. Hold on a second, did I just do that one right? Oh shoot, you know, I did this one actually backwards. Forget what I was doing here with the 21.6. We're going to come back to that because that's actually a compound voltage that's going to be inside it. It's a net voltage. We should do this one over here because this is just a winding. It's only a load. This is simultaneously a load and a source. I was wondering why my values were starting to look a little bit funky over there. So never mind what I was just doing over there. This section over here, the 2 amps that we developed, that's fine. The 18 amps that we developed going in, that's fine. We're going to start over here because this is all load section. This is load and source, so we can't just go and apply directly across it. My bad. Mea culpa. What we'll do is we'll go and start with figuring out the values of voltage that we are going to go and have over here. We can do that easy enough to figure out what we have got left across my armature. Okay, so looking at this over here, if I've got 18 amps that's going through 0.6 ohms of resistance, V is equal to I times R. I'm going to take 18 amps multiplied by 0.6, which is going to go get me to a value of 10.8 volts. So I drop from here 10.8 volts. Well, if I had 240 to begin with, and I'm going to go and drop a value of 10.8, that is going to go and leave me at a value of, now going across here, 229.2 volts over here. What is this armature voltage going to be made up of? Well, part of that armature voltage is going to go and be dropped across the value of volts that I'm going to be generating. Part of it's going to be my counter EMF that is going to be in there. So our counter EMF is going to go and kick out a bunch of it. The rest of it is going to go and get kicked out by our values of resistance that we are going to go and have inside of here. Let's figure out what we have got for our values of resistance inside of here. That's going to be that 1.2 ohms. Do I still have 18 amps that is going to go and travel through it? Absolutely. I do still have 18 amps that is going to be traveling through it. So I'm going to be able to go and take this this 1.2 ohms over here, 1.2 ohms multiplied by 18 amps. This is going to go and give me a value of voltage across the physical drop that we are going to go and have over here. So multiply those together. 18 times 1.2, which gets me to a value of 21.6. So I'm going to go and have 21.6 volts that is actually going to get dropped across the resistance of this, which means that the remainder has to be dropped. The remainder of this 229.2 has to be dropped by something. Well, the remainder of this is going to be dropped by my counter EMF. So all I need to do is take this 229.2 minus 21.6, and that tells me that the voltage that is being dropped by the counter EMF is going to be 207.6 volts that we would go and have over here. Beautiful. That's that one. I could have worked in from the other end over here. I could have started, because we did develop this 21.6 volts. I could have taken that 21.6 volts plus this 10.8 volts, subtracting them both out of 240, and come to that same value of counter EMF as well, just in case you're wondering on those. Okay, next ones that they have over here. Next ones that they're giving us here are just going to be simple word questions over here where they're going to ask you to go and figure out your total amount of watts. I've got a DC motor that is traveling at 1800 RPM, developing a torque of 40 Newton meters. Calculate the power in kilowatts delivered to the mechanical load that I'm going to go and have. Two different ways you can go and do this. You can go and work off of that 2 pi T and N one that you have over there. Alternatively, the most common one is going to go and be horsepower is equal to my Tn over 5252. What I can do is I can calculate this horsepower and then convert from horsepower down to my 700, or using 746, down to go and figure that thing out to watts. We'll quickly do it like that because it's a more common calculation. So 40 times 1800, 40 times 1800, divided by 5252. Gets me out to a value of 13.7 horsepower that I'm going to go and have over there. So that's going to be 13.7 horsepower. Well, I know that every horsepower is equal to 746 watts, so I can take that value, 13.709 horsepower, multiply it by 746, and it's going to go and get me out to a value, in this case, that is going to go and be 10,226 watts over here. Wait a flippin' minute. Does that look right to you guys over there? Well, we have to go back into our formulas for a second and say which formula are we working from over here. The one that we had over there was going to be torque in pounds-feet. This was torque that was going to go and be in Newton meters that we had over here, which is going to go and be a value of 746 over 550 as our conversion. This, what we did over here, should have been, instead of being 40, should have been 746 over 550. Should have been the multiplier that we were going to go and use for that one. So we can go and take our total answer that we have, and we can just go and divide it by this, by 746 over 550. So I'm just going to go back to this one. I'm going to say answer divide by 746, divide by 550. Delete that, 550. Which gets me out to a value of 7.54 kilowatts over here. Even I get tripped up by the stuff when we're dealing with, the Newton meters instead of dealing with the foot pounds. By and large, just watch what's going on inside of these formulas. It's super easy to grab the wrong ones. Next one that they ask you is going to go and be where they want you to go and calculate the torque developed on a shaft or motor delivering 15 kilowatts. Then they're going to go and ask you for horsepower delivered by a motor that develops a torque of 75 foot-pounds or pounds-feet that we are going to go and have, and then develop some speed and then some speed regulation ones. I'm not going to bother going through the rest of these over here because, quite frankly, it's just about 10 o'clock at night and I've been prepping and recording for you guys for far too long on this video over here. This video is once again run over top of an hour because it's our base theory that we're looking at for a complicated subject, which in this case is going to go and be my DC motors. So I'm going to leave those ones for you to go through. They are well laid out inside of your binder. Go through them, do these calculations. You will have some calculations on your exam. Just get used to manipulating those formulas. And once again, all those formulas, you should be able to find them off of your ITA sheet. All right, that is the end of this first learning task here on DC motor operating principles.